students, welcome to Sunil's tutorial. I'm Sunil Mirwani and today we'll be doing this chapter called as surface tension. Let's try to find out the reasons for angle of contact. Let's consider a solid. Let's assume this is your solid. This is the liquid which is here. This is solid. This is liquid over here. This is air, liquid. Right? Let's assume that you have a molecule A which is on the surface of the liquid, such that a part of the sphere of influence is in the liquid, in the air, and in the solid. Right? Now, let's try to see the forces that are going to be acting on it. One, the force, since a part of the sphere of influence is in the solid, there is going to be a force that will, or there would be a tension that would be acting from the solid. Then, since a part of the sphere of influence is in the liquid, there would be some tension that will be acting towards the liquid. Let's call this as P. Let's call this as Q. Right? We are doing explanation of angle of contact. Now, let's consider a liquid molecule. Consider a liquid molecule A which is situated on liquid surface. Right, and in contact with the solid. In contact with the solid. Right. Now, let's try to understand the forces that would exist here. The sphere of influence of molecule A is partly in the solid, partly in the liquid, and partly in air. I can say that the sphere of influence of molecule A is partly in solid, liquid, and air. Right? Now, the molecule A is acted upon by three types of intermolecular forces. Since you have its sphere of influence in three different areas, therefore I can say that molecule A is acted upon by three types of intermolecular forces. First, there is going to be a force of attraction that will exist between molecules of solid and the molecules of liquid. Now we know that molecules of different substances attract each other. This force of attraction between molecules of different substances is called as adhesive force. That means there is going to be some adhesive force between the molecules of solid and the molecules of liquid. Right? So I can say that adhesive force which is exerted, adhesive force which is exerted by molecules of solid right, the resultant of this force is perpendicular to the surface of the liquid, surface of the solid, perpendicular to the surface of the solid. That's your AP vector. This is A. So AP vector, which is perpendicular to the solid and is represented by my AP vector, right? So that is the force that is going to be exerted by the solid on the liquid. Next, two molecules of liquid will attract each other. The force of attraction between molecules of same substances is called as cohesive forces. So there is going to be some amount of cohesive forces between molecules of liquid. So second force that will exist is the cohesive forces. Cohesive forces exerted by the molecules of liquid. Exerted by molecules of liquid. Right? Now the resultant force is inclined. This particular force of cohesion between molecules of liquid is inclined at 45 degrees. Is inclined at 45 degrees to the surface of the liquid. Question: so why 45 degrees only? Right? Because there is going to be an equal amount of adhesive force exerted by molecules of solid. Right? So total is 90 degree. There are some molecules that are being attracted by molecules of solid. There are some molecules. This is solid. This is liquid. You have molecules that are being attracted on this side. Equal number of molecules being attracted on either side, and that's the reason why this angle is going to be 45 degree. Fine, do we get this thing clear? So the resultant force is going to be inclined to the surface at an angle of 45 degree. This force is represented by AQ vector. The third force, there is going to be some adhesive force between molecules of liquid and molecules of air. So I can say that adhesive force is exerted by air molecules, right? Now since the number of molecules, air molecules in the sphere of influence of A are extremely small and less, therefore the resultant adhesive force due to the air molecules is negligible. You can say since the number of air molecules in the sphere of influence of molecule A is very small, therefore the resultant adhesive force is almost negligible. Okay. Now, so these are the various forces. Now, in addition to the intermolecular forces, there is going to be gravitational forces which will be equal to the weight of molecule, which will act in vertically downward direction, right? But this force is also very small as compared to the strong intermolecular forces, and therefore I can consider it as negligible. That means the behavior of molecule A will now depend only upon two forces, that is AP vector and AQ vector. I can say that behavior of molecule A behavior of molecule A now depends on the resultant of two forces, that's AP vector and AQ vector. Right? Now, when the liquid surface is in equilibrium, the free surface of the liquid always remains perpendicular to the resultant forces. How do I know that the liquid surface is going to be at equilibrium? At equilibrium, the free surface of the liquid remains perpendicular to the resultant force, Fine. Now let's see what are the cases that you can have, right? That means the liquid surface in contact with the solid must remain perpendicular. You can say therefore the liquid surface in contact with solid must remain perpendicular to AP vector and AQ vector. So these are the forces that will determine the angle of contact. Now let us consider case 1. Now case 1, let us consider that the liquid partially wets the solid. If the liquid partially wets the solid, right? Now in that case, let's see how would the diagram be. If the liquid partially wets the solid, in that case your diagram would be, this is your solid, this is your surface of liquid, you have point A, sphere of influence, you would have a force, that is your, you would have an adhesive force, that is AB vector, you would have a force at 45 degree, this is AQ vector, right? Now it has to remain perpendicular to the liquid surface. Now that means I would have a resultant force here somewhere AR vector, right? So that means if it partially wets the solid, I can say that the resultant adhesive force is quite large as compared, the resultant adhesive force is quite large as compared to the cohesive force. That is, I can say that therefore AP vector is greater than AQ vector, right? If the liquid partially wets the solid, that means the cohesive force is going to be more than the the adhesive force is going to be more than the cohesive force, and therefore the resultant AR vector will AR vector lies outside the liquid, right? This is your liquid surface, right? So in that case sorry, AR vector lies outside the liquid. Now in order for AR vector to be in order to be perpendicular to AR vector, in order to be perpendicular to AR vector, we said that at equilibrium the liquid surface should be perpendicular to the resultant vector. In order to be perpendicular to AR vector, the liquid molecules like A move upwards. Liquid molecules like A move upwards, right? And the resultant is, as a result of it, as a result of it, because of this, the liquid surface becomes concave. Liquid surface becomes concave. So that is the reason why the liquid surface becomes concave, right? Next, let's consider case 2. Now, case 2. If the liquid does not wet the solid, if the liquid does not wet the solid, if the liquid does not wet the solid, that means in that case the cohesive forces will be more than the adhesive forces. If the liquid does not wet the solid, this is your solid liquid, you have solid here, this is liquid here, two forces, this is going to be my AP vector, this is going to be AQ vector, right? Now if the liquid does not wet the solid, in that case you will have AQ vector will be greater than AP vector, fine. If the liquid does not wet the solid, the resultant adhesive force AP vector is small as compared to cohesive force AQ vector, right? So the resultant AR vector would therefore lie in the liquid. This will be AR vector, therefore the resultant AR vector would lie in the liquid, right? Now if it lies in the liquid, you would have, in order to be perpendicular to AR vector, in order to be perpendicular to AR vector, liquid molecules like A move downwards right. As a result of this, you would have a convex region formed. The liquid surface becomes convex. Liquid surface becomes convex, right? Case 3. If it partially wets the liquid, if it does not wet the liquid, third, if the liquid completely wets the solid, if liquid completely wets the solid. If the liquid completely wets the solid, obviously the resultant adhesive force is going to be very large as compared to the cohesive force. Therefore, the resultant adhesive force resultant adhesive force AP vector is very large as compared to cohesive force AQ vector, right? So as a result, the resultant AQ vector therefore gets neglected. AP vector, guys, is very large in that case as compared to AQ vector. Therefore I can say that the force AQ vector can be neglected, hence AQ vector can be neglected, right? Once I can say that AQ vector is neglected, therefore the resultant force AR coincides with AP. Therefore resultant force AR coincides with AP. But AP is, as it is perpendicular to, I can say that coincides with AP, and as a result the liquid surface in contact is almost tangential to the solid, and therefore there will be no angle of contact. AP is as it is perpendicular to the solid, right? So it is going to be tangential to the liquid surface. As it is already tangential to the liquid surface does not have to curve, so that the liquid molecules become perpendicular to the resultant force. Fine. I can say therefore the resultant AR is I can say that straight away. I can say therefore liquid surface in contact, the liquid surface in contact is almost tangential to the solid surface, and therefore the angle of contact is 0. So these are the three cases, and that is the reason why you have an angle of contact. And do we get this in here? Next. So this is the reason why you have angle of contact. Next, let's see the next thing. The next thing that you have is capillarity. Now, ordinarily you would have the free surface of liquid that would remain horizontal, but due to angle of contact phenomena, the liquid surface sometimes either becomes concave or convex, which I just explained to you. Right? Now, if the vertical section of these liquids is very small, if the surface area of these liquids is very small, then the effect is more pronounced, right? See, I can say that ordinarily the free surface of liquid remains horizontal. Free surface of liquid remains horizontal, right? But due to angle of contact phenomena, it sometimes becomes concave or convex. The liquid surface sometimes becomes concave or convex, right? Now let's consider the forces of tension. The forces of tension act at right angle to the surface. Now let's see a couple of diagrams to explain this. Ideally, it should remain straight. This is my surface of the liquid. The forces acting on it are, this is P, this is Q. I'm taking a section of the surface of the liquid, two forces acting on it. You would have a force PT and you would have a force QT. So you would have equal amount of tension acting on either direction, right? But due to angle of contact phenomena, sometimes it so happens that you would have a surface like this. So the forces have to be tangential. So you would have one force tangential here, one force tangential here. So this is, and this force would try to move upwards. So you would have same section PQ, right? Tension acting outwards, tension acting outwards. Again, this is due to angle of contact phenomena. I could also have convex region. The forces have to be tangential to the liquid surface. So in that case, you would have T tension on either side, same section PQ. Ideally it should have remained straight, but due to angle of contact phenomena, you would have either a concave region or a convex region, right? Now let's say that let PQ be a small section A. Let PQ be a small, let us assume that PQ is a small element of the area, of the surface of the liquid. Right, in which case I can say that let length PQ be unity and let it be perpendicular to the plane of the figure. Let length PQ be equal to 1. I'm considering a unit length section of the area. So I'm considering a small element of the area of the liquid surface of unit length, and let us assume that PQ is perpendicular to the plane of the figure. Right? In which case the forces due to surface tension will always act right angles to the boundary of the element PQ. The forces, so that the body remains at equilibrium, the forces of tension will always act, the forces of tension will always act at right angles, will always act at right angles to the boundary, of element PQ. Right? Let's consider case 1, the first one. Right? If I consider case 1, the liquid surface is plane, then the forces of tension will act in both sides of PQ will be equal if the liquid surface is plane. If liquid surface is plane, then the same amount of forces of tension will act on both sides of PQ. I can say that the forces of tension, then the forces of tension on both sides of PQ will be equal. The forces of tension on both sides of PQ will be equal. Now, as a result of this, there is going to be no difference in the pressure and the two sides, there will be no difference in the pressure on the two sides of the plane surface. Therefore, there will be no difference in pressure. There will be no difference in pressure on the two sides of the plane surface. two sides of the plane surface. That's case 1. Case 2. Let's consider that the liquid surface is concave. If liquid surface is concave, now that's this diagram, the second diagram, right? If the liquid surface is concave, then the resultant surface tension acting on element P, the resultant of the surface tension acting on element PQ acts vertically upwards. Concave region, you have tension acting perpendicular to the surface, tension acting perpendicular to the surface. The resultant of these two forces is going to act vertically upwards. So if the section PQ is concave, at point Q there would be a force, there would be a tension. At point P there would be a tension. At point Q there would be a tension, and the resultant of the two forces will act vertically upwards, right? So I can say that the resultant surface tension acting on PQ, the resultant surface tension acting on PQ, the resultant surface tension acting on PQ acts vertically upwards. Acts vertically upward. Now, since the liquid surface is at equilibrium, since the liquid surface is at equilibrium, it counterbalances this resultant force. It counterbalances this resultant force, right? As it counterbalances this resultant force, there is a pressure that acts on the concave surface and makes the concave surface even greater on the other side. I have a force that is acting vertically upwards due to the resultant of PQ, due to the resultant of the tension at point P and Q. Now the liquid is already at equilibrium. To counterbalance the force, there has to be a downward force that will be exerted. Now because of that downward force, what will happen is that the concave region will become even more curved. That makes the concave region even more curved, right? So I can therefore say that in order to counterbalance this, the liquid surface at equilibrium counterbalances this with a resultant force, and the pressure from below must be greater than the pressure from below must be greater than the pressure from the other side. Then pressure from other side, right? So that's the reason why you would have the pressure acting on the concave surface becomes greater, and therefore it becomes even more concave. Case 3. If the liquid surface is convex, liquid surface is convex. If the liquid surface is convex, the two forces acting on it, one, this is one force that is acting vertically downwards, then you have another force tangentially acting vertically downwards on section PQ, right? Downwards, right? The resultant of these two forces is going to be in downward direction. To counterbalance this force, what will the liquid do? The liquid will exert even a greater force in upward direction. The resultant of these two forces is in downward direction, right? To counterbalance this force, because the liquid is already at equilibrium, to counterbalance this force, the liquid exert a greater force in upward direction. So I can say that in case of convex surfaces, in case of convex surfaces, the resultant of the surface tension forces, the resultant of surface tension forces, the resultant of surface tension forces acting on PQ act vertically downwards in order to counterbalance the resultant force, in order to counterbalance the resultant force must act in vertically upward direction from below must push the liquid up, and therefore the region becomes even more convex, right? Now, from this what we understand is that in the case of a plain liquid surface, there is going to be no difference on the two sides of the liquid surface. In case of a curved liquid surface, there is going to be a difference in the pressure of the two sides of the liquid surface. There is going to be a difference in the pressure of the two sides of the liquid surface. The pressure on the concave side is greater than the pressure on the convex side. This result plays an important role in the capillary action. This is what leads to capillary action. Fine, do we get this in clear? So do we understand why we have capillary action of the liquid? The capillary action of the liquid is because the resultant of the two forces either acts in upward direction or downward direction. Fine. Okay, we'll stop this here for the day. Thank you very much.